Hi everyone, I'm Ria Jo, a student at Cary Academy in North Carolina, and today I want to talk about a problem at the intersection of machine learning and healthcare equity and a system I built called ChipFL to help solve it. So here's the situation. Hospitals can't share patient data because of privacy regulations like HIPAA, which makes it really hard to train AI models that generalize well. Federated learning was designed to get around this. Hospitals train locally on their own data and only share model updates, not patient records. But it still has two big problems. First, hospitals are just different. Different patient populations, different protocols, and different volumes, so treating them all the same is a mistake. Second, large academic hospitals end up dominating the model updates, so smaller community hospitals get weaker AI tools. The hospitals with fewer resources end up with worse technology. That's the structural inequity ChipFL is designed to fix. In standard federated learning, a central server sends out a model, each hospital trains locally and sends back updates, and the server averages them and repeats. It's grown a lot as a research area, with over 250 papers in federated learning since 2018, but the equity problem has largely gone unaddressed. So what does ChipFL actually do differently? Well, firstly, the name stands for client clustering, hierarchical aggregation, and personalization, and it works at three levels. At the macro level, before training starts, each hospital is represented by a vector capturing dataset size, mortality rates, and missingness. We cluster the 208 hospitals into 5 groups using k-means, grouping similar hospitals together. At the meso level, during training, each hospital is pulled slightly toward its cluster peers while staying anchored to the global model. This prevents any one hospital from pulling the whole model in its direction. At the micro level, after training converges, each hospital does one round of fine-tuning on its own private data. No extra communication is needed and no privacy risk as well. Methods like fedaverage, fedprox, and scaffold have each made progress on pieces of this problem, but none of them address heterogeneity, fairness, and personalization together. ChipFL is the first to tackle all three jointly. I used the eICU database, over 200,000 de-identified ICU admissions across 208 hospital units in the US. The task was predicting in-hospital mortality. I also used inverse square root weighting during sampling so that smaller hospitals get proportionally more representation each round. Here's where things get interesting. ChipFL reduces size-dependent bias by over 90% compared to fedprox. The size bias coefficient goes from negative 0.032 down to negative 0.002, nearly zero, and it does this while maintaining a competitive AUROC of 0.903. Fedprox hits a higher peak AUROC of 0.933, but at the cost of dramatically worse equity. Larger hospitals benefit and smaller ones are left behind. ChipFL trades a small amount of average performance for a model that's genuinely fair across institutions. To visualize the full trade-off space, I ran a Pareto frontier analysis across three axes: mean accuracy, worst decile robustness, and size bias. No single method wins on all three simultaneously, but ChipFL consistently sits in the fairness optimal corner. If equitable deployment is the goal, Chip is where you want to be. 4 quick takeaways. There's a real trade-off between accuracy and equity, and it has to be acknowledged. CHIP nearly eliminates size bias without sacrificing clinical usefulness. Personalization and hierarchical regularization actually work together, not against each other. And fairness is not one thing. Tail robustness, distributional inequality, and size bias are three different definitions that lead to different algorithmic choices. This matters beyond benchmarks. If federated models systematically underperform for smaller, rural, or under-resourced hospitals, that is a healthcare equity issue, not just a technical footnote. ChipFL treats federated learning as a coordination problem rather than a pure statistics problem, and I think that shift in framing matters. A few honest limitations. This is logistic regression only, clustering is static, and everything here is simulated federation. Next steps include adaptive clustering, deep learning extensions, multi-seed evaluation, and eventually measuring fairness through actual patient outcomes rather than just model metrics. To sum it up, ChipFL shows you do not have to choose between accurate and equitable AI, but you do have to be intentional about it. So I hope this sparks a conversation about what we are actually optimizing for in clinical AI adoption. Thank you so much for watching.